Okay, hello everyone. Today, during M-Plan's paper club, we are talking about a paper called Deep Graph Infomax, relatively old paper, considering that the first GNN was published in 2016-17. But it's actually quite interesting because it's about learning unsupervised, learning in an unsupervised fashion on a graph, so that we get graph embeddings, node embeddings, and that those we can later use for downstream tasks. We'll talk about the idea of the paper, a bit of theory. This was published in ICLR, so there has to be some theory. The theory is really motivation why this makes sense, and then we'll look at experiments. Not all experimental results are amazing, but they are good enough, considering that we are doing unsupervised learning here, and then comparing those with supervised models, right? Okay. Let me zoom in a little bit more here. Yes, better. So there is a bit of introduction. We don't need to talk too much about GNNs in general, because we have done a fair number of papers about learning on graphs. But in terms of introduction, what we should add here is that usually when you are doing a node classification on a graph, the learning objective is classification, and you have labels. So there are, generally speaking, two settings, transactive and inductive settings. So the first case is when you have one massive graph, some of the graph is labeled, you're trying to predict the rest of it. Those are things like citation networks, social networks. Basically, it's one massive graph. The other case is when you have many different graphs and you learn a model on one set of graphs, and then you do inference on a new graph. So this is important, and in some ways a harder problem, because we need to learn to predict on unseen graph structures. So we'll see later on how this changes the propagation mechanism in the graph. So there is also a bit of mention about random walks. So those were the state of the art about when it came to learning on graphs before GNNs. They are still related. You can find relationships between those two approaches, but random walk-based methods are also similar to non-learnable algorithms like PageRank. You can motivate PageRank as a random walk, random walk calculation. But we'll look into those a bit in some more detail when we discuss the paper, the algorithm presented in the paper. The main idea here is that when we are learning, the main contribution is that we want to fix or improve on a limitation that comes with all other GNNs, really, which is your node embedding has information at most from its neighbors. Right? If you have a 3-layer GCN, the current node gets updated from 3 hop neighborhoods. So it does not have information about the overall graph structure. Okay. So what we want to do here is to add information from the entire graph structure. And obviously, we don't want to have a massively huge. We don't want to just average everything, right? We could argue that we can average all embeddings in the graph. It will have information from everywhere, but then you will have the same embedding for all nodes. So we can't really do that. On the other hand, GATs, graph attention networks, in principle allowed also using information beyond the neighborhood, the immediate neighborhood of the node, which was actually written by the same research group, pretty much same authors. But they're also we have the problem with over smoothing, as in all nodes end up with similar embeddings. And more importantly, here we want a non-supervised objective to learn. And the idea is that we will do contrastive learning. But before we talk about that, any comments, questions here about the introduction? Okay. So that's all good. So the related work part is all about contrastive methods. Because this is also a contrastive method. Contrastive means we want to learn, we want an objective that that's minimized when we compute distance or a scoring function between two similar nodes, two similar embeddings or feature vectors, all the same things, and maximize it if the feature vectors are very different. For example, if you take two different graphs and get a summary vector, we'll discuss how it's computed later on from both of them. If they are different graphs, the summary vectors should be different. If you take neighboring nodes, we have an assumption that their embeddings should be somewhat similar. There must be something similar about them, which is why they are neighbors, right? So the objective function we construct is based on this contrastive idea. There is a mention about the sampling strategies, which is also a way of doing contrastive learning, because basically you can see the so you can if you do a comparison between word embeddings, we could say that if you take a random walk in a graph, that it would become a sentence, and each node would represent a word, and then we could formulate the problem as one of the older word embedding methods in a similar setting, and then we would have to do something to get a random walks, right? Because it's random. So they're trying to show the relationships here. The other method they mentioned is this predictive coding one, which is also a contrastive method, a contrastive predictive coding. Well, as the name suggests, it's also contrastive. So the idea is that, well, the idea here is that methods are all, so the CPS methods are all predictive, which means they are also supervised. Here, in this paper, the methods are different because here we contrast global and local parts of the graph at the same time, simultaneously. And the global variable is computed from the local ones, as I mentioned before, using a mapping, a one-to-one mapping from the graph to its embedding. I guess we can continue to the methodology unless there are any comments here. Did I miss anything? Oh. Cool. So let's talk about the deep graph Infomax. The deep, that's, by the way, the term deep is a bit exaggerated.
Yes. Vahan, I had a question.
Yes.
At the very end of related work, it says both methods rely on matrix factorization style losses and are thus not scalable to larger graphs. So why are they not scalable to larger graphs?
Because factorizing matrices is expensive. I think it's cubic usually. So if you have a massive graph, getting matrix would be the adjacent matrix from your graph. Factorizing the adjacent matrix would be very expensive or not possible.
No online methods to do this? I would have thought that there were some methods that are online because the number of subgroups you're essentially learning are limited in size, right? So
But there probably are good ways to do matrix factorization, but it's an expensive problem, and you will have to find either sampling or problem-specific ways of doing it. I'm not entirely sure, but in general, matrix factorization is computationally expensive, isn't it?
Yeah.
And so an example of matrix factorization would be like SVD, right?
Yes, but you can also do upper triangular and what's the other one? You get upper triangular multiplied by orthogonal matrix. It's another factorization. I forgot the name right now, but usually you want basically to represent your matrix as a multiple of two other matrices. SVD would be 3 matrices. QR, yes, thanks, Alexander. Yeah. Okay. But the problem is finding those factorizations can also be turned into non-convex problems. Anyway, okay, so let's continue studying the method. Setting is the same. We have node features in X. Each, well, between 1 and n is the number of nodes. You have also a graph given by the adjacent matrix. In general, it can its elements can be any real numbers. You can even have edge features. But normally, in all experiments here, actually, all experiments in this paper, we have unweighted graphs without edge features. Simple. And I think, well, you can have directed or undirected. PPI is not directed, but citations are directed. So it depends. Either one can happen. And we also, our objective is to learn an encoder, which takes an input, the feature vector, adjusting matrix, and finds a matrix of encodings where each row represents the encoding for the given, for the corresponding row in X.
I had one question. This F prime, right? Does it have to be actually smaller than the actual number of features? Because
prime.
Yeah, because even though it's an encoding, right, you could think of also encoding neighboring information, right? So if you make F prime large enough that you sort of summarize not just the node, but also its potentially even properties, right? Yeah,
so I think we may not mention F prime explicitly, but when we talk about the invertibility of the matrix of the graph embedding, it might be related, because if you make F prime too large, and then you may not be able to make the mapping between the graph embedding and the node embedding one-to-one, right? Because if F prime is large, you may be able to reconstruct it in back. You may not be able to find that one-to-one mapping.
One-to-one mapping between the whole graph and the nodes, or just node to node? Because you could imagine if you have like a symmetry in your graph where one node, where two nodes are exactly equal, you would want that, right? You would want a one-to-one mapping.
Yeah, that's another thing that was also mentioned here later. The Valser. Let me say it correctly. Valser's what there is the graph isomorphism problem, right? The isomorphism test, which exists in which basically all GNNs fail. If you have a symmetric graph, you end up with the same embedding. You want it or not, that's how these methods work.
Yeah.
Yeah, but actually, but so far we haven't said anything about F prime. It depends on our methods at the end, really. Okay. So so we are going to train a model. Our objective is going to be maximizing local mutual information, which means we need to find node embedding that also captures the global information from the graph using the summary vector. S is the summary vector. We'll talk about it later. So the way they go over the paper is give a high-level idea and then build down into more detail and then more detail and then more detail. So we always start with the higher level, and then we'll discuss the details in a bit.
I have a quick question.
Yes.
So it says what you try to generate. So in the paragraph just above where you are now, just above 3.2, it says so you produce sort of patch representations instead of sort of like node embeddings. Is there some explicit way to choose sort of the size of the patch that you're trying to sort of get the patch representation for?
Yeah, good point. I should mention this because they talk about patch representations because they want to emphasize that the node embedding contains information also about its neighborhood. It's not only the node's embedding, but it represents the entire also information from its neighborhood. So normally, if you have a 3-layer GCN, you would have 3-hop neighborhood, and that would be the patch. That's how I understood it.
Okay. Yeah.
Because it's a patch of the graph centered around node I. So if you have 3 layers, you have 3 hops, 3-hop neighborhood. Okay.
Yeah.
But that's what they say. In what follows, we will often refer to HI as patch representation to emphasize this point. So normally you would call this as a node embedding, but because it contains information about the neighborhood, they call it patch representation. Okay. Right. Back to the learning objective. So as I said, we will have the summary vector S. We will use that. We will also have the readout function R, which takes in the output from the encoder. So epsilon is the encoder, which takes the node embeddings, node features, sorry, just symmetrics, gives an encodings for each node, and then we give it to the readout function, and it returns us the summary vector for the whole graph. We can see this as the graph's representation, graph's embedding. Okay. So that contains the global information. They're also going to use a discriminator function, which takes a patch representation, node embedding, and the summary vector, and computes a score between those two. Okay. And we are going to also use the discriminator in our objective function.
Yeah. So when we say patch representation, it would be the embedding of a single node, and just because the embedding uses say 2 or 3 hops away, it sort of represents a patch. Is that correct?
Yeah, okay. That's how I understood it. Yeah.
Okay. Cheers.
I think that's what they say up here.
Okay.
And of course, to have to be able to learn in a contrastive manner, we need positive and negative samples. The positive ones we already have in the graph. So if you have a node, we have its neighbors. Each neighbor, we have a node, and it belongs to the graph. That's a positive example, positive sample, right? Yeah, that's why you have this agendized, and you want to minimize the discriminator for those. However, we also want negative examples, so that if a node does not belong to a graph, then they get a large score. Actually, no, low score, because we compute the mutual information. So discriminator would be low then. So we need to construct also negative examples, which we can do by, there are a few actually examples, see how we do it. Basically, you take the graph, you modify it, you do random changes to the graph, and then compute the summary vector, which for those, then those give you the negative examples. Yeah.
And the idea here was that you originally only start on a single large graph, and then you sample the positive samples from that, or they also mentioned multi-graph settings at some point. I was not quite sure what really the distinction there is.
Yeah, so it depends, right? Because if you have only one large graph, then you have only one graph, and then when you modify it, you compute the summary, you get a negative example for that. But you can also change so actually the way they modify it, they shuffle the order of embedding of feature vectors, which means graphs get different, nodes get different features. But if you have multiple graphs, you can do it either inside each graph, but you can also, I think they only do it inside each graph, because you could also, in principle, assign a summary vector from one graph to a node that doesn't belong to it. I think what they do is they do the shuffling inside each graph.
So the nodes, if you look at the nodes in isolation, they are still the same, just at a different place in the graph.
I think so.
That's what they did for the I think what they called like the transductive setting. So they take a graph and they just shuffle the nodes and keep the same adjacency matrix. But that's not like the method they're proposing. That's a method of corrupting the graph that they suggest. Vahan, I guess we haven't gotten to that point. I wanted to ask, I had a couple, one thing I wanted to talk about, but I think, have we gotten to the training objective that they're introducing or not yet?
Almost.
Okay, I'll wait for that.
Just getting there. You mean the equation 1? Yeah. I think we are getting there. Well, basically we introduced positive and negative samples, and then we introduced the objective function, which is binary cross entropy. If you look down here, we have two sums, expectation over the positives with the log, and then log 1 minus the score with over negatives here. And then it's also normalized. Peter?
Hey,
yeah.
So actually it wasn't necessarily a question, but I was just, well, it's a question, what do you guys think of this? It's more like, to me, the last line where it says, note that this is a reversed version of the argument by this author. For node classification, our aim is for the patches to establish links to similar patches across the graph, rather than forcing the summary to contain all of these similarities. So to me, a major distinction between previous methods and this one is essentially using neighborhood similarity between distinct parts of the graph to learn representations, whereas the other one was saying like nodes close to each other should be have similar representations. So they are very fundamentally different, because you could have two subgraphs that are very far from each other within the same graph that you'd want to have the same representation with this method, but with the previous methods, you wouldn't care. So I was thinking that's like a fundamental difference of this method. And my question to everyone is just, what do you think of this difference? Do you think this is a more informed or a better way of learning graph representations, or no opinion or whatever?
I don't know very much about it, but I was thinking that here's a lot of tuning that you sort of do by choosing your corruptor, right? The moment you say that you shuffle the nodes, essentially what you're saying to the graph, please don't look at the content of the node, because the content of the node is still the same over all the graphs, right? So you're sort of telling the algorithm implicitly to look at the connections, right? But of course that is purely an option. So I wonder how much, yeah, I don't want to say tuning, but how much choice there is actually in parameterizing this unsupervised method. Because you could, for example, also create a sample graph where actually the thing you keep the same is like you create new nodes where, say, the difference to neighboring nodes is the same, and then you completely erase that sort of information for the discriminator to decide against. So you would learn a fundamentally, I think, very different representation.
That to me was they say it in the graph in the method that like how you corrupt the graph is based on what information about the structure of the graph you want to encode.
Yeah.
So that would probably take a lot of domain knowledge in order to figure out what's the correct way, or maybe just like domain knowledge of graph structured data, maybe not the specific domain itself. I was thinking it would be interesting to hear about different corruption functions and like what they're helping the model to learn about the graph. Definitely. Here, they're essentially changing the edges in the graph when you're changing the nodes order.
Yeah, you can see that way, right? You can also see changing the edges. But interesting thing I noticed is both discriminators have the same summary vector, right? So basically, you're only changing the nodes embedding the patch representation and saying, well, this patch should be in this graph, but this other one should not.
It would be perhaps interesting to have like a sort of, I don't want to say ablation studies, but you know how you here have the second part is x tilde and a tilde, right? But actually you could decompose it as one where you leave x the same and only change a to a tilde, or leave the adjacency the same and change x tilde, and then maybe like empirically study how the resulting discriminators look like, and what are these discriminators suddenly focusing on.
Yeah. Well, I guess you can also say the more you shuffle, the better, because you're trying to find a very different examples for negative case. So you just shuffle as much as you can, and then should hope it's okay.
But then why shuffle? Why not completely randomize everything about it?
Well, because later on you're going to do classification tasks, right? So classification means you will see the same sort of nodes, but you don't want to shift the distribution. That's my guess.
Yeah, that's what I was confused about, because they could just choose, because they shuffle the features for each node, they could just choose sort of random features.
No, they don't shuffle
those as negative samples.
They don't shuffle the features. They
really? Oh, okay. I thought that's
so. Okay. I think they only move features from one node to another. So that's how I read it somewhere here, that they only shuffle the order.
Okay.
I think so. I can search after at the end to make sure that maybe now. 1 moment. Yeah, I can't. There is no search function here. Okay, so that's my guess. Yeah. If they make it completely random, you might end up like with a distribution shift, and then not sure if it's, maybe you can add that, right? You can also do that, because the more you have here, the better. Why not? Right? You can do all kinds of shuffles there. Because this M can just be very large. Okay, let's look at a bit of theoretical motivation. We won't go into details of the proofs, but there is nothing excessively difficult, to be honest. If you follow the steps, it's actually reasonable. But the idea is that first we find the error bound, an upper bound for the error achieved by an injective. Injective means one-to-one mapping. Injective readout function, and first we show that there is an upper bound on the error, and then if R is injective, and then injective, and then since then after here we will assume that R is injective, and then which will allow us to get inverse functions and follow with the rest of the proofs. I don't know.
Can I ask a quick question?
Yes. Yes.
So injective means that if the graphs are different, they have a different S essentially, right?
Not the graph, because R takes the encoding as input, right? Takes the encodings of like it takes a matrix.
So if the encodings are different, then the
also the graph, right? If the whole matrix is different, so R takes the R takes the feature vector X. So not the representations drawn from empirical probability distributions. So X, K's are, yes, those are the representations, and R takes the representations and gets the summary vector. So which means this injective means R is a one-to-one mapping. You can inverse.
Yeah. Okay. Yeah, I was thinking that maybe, I don't know how reasonable. Anyway. Okay. Because I thought there was some logic that they had later on that was talking about like maybe S's could be the same for different graphs, but maybe I need to reread the proof.
Well, it can't be. That's the assumption they make. S can't be. Yeah, exactly. So if you change the embedding or the graph structure, S's are different. That's the main assumption. I don't know how real it is in real life, but first,
because their readout function is a summation.
In the simple case, yes, they are saying, oh, because the graphs are simple, we can we can average them or sum. But they also point to a couple of more advanced methods when your graphs get more complicated, larger, especially larger. Because if you have a massive graph, averaging will likely end up with the same graph, right?
And is a choice of R similar to choosing like the distance metrics in a distance in a classic unsupervised problem, right? So you also would expect that this pushes your solutions to different corners or different results. Yeah.
They mentioned at the beginning that Infomax is borrowed from a convolutional neural network. There was a paper about Infomax on CNNs. Here they extend the idea to graphs. But yes, I agree with that argument. Right, and then basically we show that the error is bounded, and then this point, this half upper bound on the error is an upper bound, and this half is actually only can happen only at the very stupid cases. So if there's a constant readout function, right? So if the readout function is constant, then we are not learning anything. But basically, we have guarantees that there is an upper bound on the error. Important corollaries is that
is it useful because the upper bound is a constant, right? It would be if the upper bound was a function of your graph and you can make it smaller and smaller, that would be probably more useful than
yeah, sure, like inverse of the graph size or something.
Yeah,
but it can't be because the larger graphs means it's harder to make R injective.
Yeah, of course you could always like normalize your error function like as a error per node or so, and then then it would be hang on, actually that is true, right? Because if the error function is smaller than 1/2, but it's if you look at the definition,
the error function is
but it's
the average error.
Is it average or is it the?
No.
It's not the average, right? So
no, it's the sum of.
Exactly. So you would expect the average error to actually do go down, right?
So between the joint distributions. Oh, they also use this lemma to justify that using the product of marginals makes sense, but we'll get to the theorem later.
Yeah.
So there's some squares of probabilities halved. Well, obviously this can't be more than 1 because it's the sum of probability squares.
It can't be more than half, and it can't be. And you also know that the least possible, each S, the smallest possible probability it can have is 1 over the number of like the set of X.
That's the other bound, right?
Because it's the top of the lower bound would be cardinality of X squared divided, or no, 1 anyway. Cardinality of X squared divided by cardinality of X squared squared.
What was actually the probability of SK again? That was the probability that this patch summary is no, sorry, what? The patch summary is coming
like it exists. It exists, like it's part of the distribution. Like you have a since you have a distribution over the feature matrices X, and you can go from X to S, you can also have a distribution over S. So it's a probability of S appearing in whatever problem setting it is.
Yeah. So given you have a graph, you get a representative summary function output.
Vector, or vector.
It's a bit of a hard concept to really wrap your head around.
I was wondering why they use the notation S with an arrow pointing to represent a vector instead of using bold S.
Well, for all vectors, they use arrows. This is another way. They just use arrows. Matrices are bold. Anyway, let's go look at the corollaries. So here, they define the S star, which is the optimal summary under the classification error. Let's say we found the optimal summary of an error of an optimal classifier between the joint and the product of marginals. Then the size of the optimal summary vector is the cardinality of the optimal summary vector is the same as for the feature matrix. This basically can be shown because we already know one side of the inequality, the other one we can show using Jensen inequality? No. Using the fact that R is injective, because we can invert and then we can show here, but we don't need to go into details here.
So that's essentially just saying that the moment you choose S smaller than the absolute size, you have some form of compression going on, which
exactly is because of R's injectivity, right? That's the main part. Yeah.
In a sense, that it's sort of trivial, right? You would expect it would be very surprising if that would be different. Right?
Yeah. The next one is well, they're saying that
is the error the error of between the graph level representation and the patch representations that they have?
Error. Oh, this error.
Yeah.
It's this error bound here, which is the assuming the class balance has an error rate upper bounded by error. So the error rate is the optimal classifier between the joint distribution and the product of marginals. Right? It has an error rate. So basically how non-perfect the objective is. There's error from the objective.
Okay, yeah, sorry, because I got a bit confused because later they do the argmax of the mutual information, but yeah, sorry.
Well, there's the theorem. The theorem says the optimal summary is the argmax of mutual information between the feature vectors and the well, over S. Argmax is over S, right? So if you find the summary vector that maximizes the mutual information with the feature vectors, that would be the optimal summary vector. And you show it again using that R is invertible, and well, and properties of mutual information and entropy, which is the same. Entropy is the mutual information between X and itself. Right? Basically, there's just these definitions. The other theorem, again, that motivates this whole thing is that the patch representations that minimize the classification error between the probability of agent S and the multiple also maximizes the mutual information between the feature vector and the patch representation. So this is why they motivate using the patch representations. And the proof again relies on the invertibility or injectivity of R. Okay. Any more comments here? Okay. A bit of theory, but it's okay, right? Sometimes we do theory also. Next, let's quickly summarize the steps of deep graph Infomax. Basically, first we get the corruption. We took the corrupted features and the just symmetrics, and then we pass it through the decoder, get the representations, the patch representations, and then we get the patch representations for the negative samples with the tildes. Then we compute the summary vector, and then we update the encoder, readout function, and also the discriminant, all of them together, by doing a gradient pass to minimize the objective we saw before. Okay, and then that's how we learn all three of them. There's also a diagram. We refer to this. Basically, there is positive examples on top, negative examples in the bottom, using the same encoder, same summary vector, using the readout on the positive graph only, and then we pass those into the objective function. Comments? Okay, a bit of experimentation. So they use the Cora, which is the paper citations, another citation network, PubMed, another citation network, Reddit is the large inductive learning one, and PPI is the tiny one. PPI is the protein-protein interactions network. Those are inductive, means those are multiple graphs. The top three are one joint graph. You can see that Reddit is massive, which means they had to do clever sampling to get it to get the model to train on the Reddit data on the GPU, because they didn't have enough memory. Features, edges, number of classes. Interestingly, PPI is multi-class binary, which means there are 121 classes. Of each of them can be 0 or 1. Everything else is a normal classification. And the test is that because we also have labels for all of these, the test is the hypothesis is, can we train a very simple classification model? In this case, it was logistic regression, using the pre-trained node embeddings as input features, and compare it to the classification we get out of any of the state-of-the-art at the time state-of-the-art GNNs using supervised GNNs using the existing labels here. So there is a bit of conversation about the transductive learning. Basically, this is the normal GNN update. Degree matrix, normalized degree matrix. This is the Laplacian. And then there is a non-linearity. Theta's are the learnable weights. We have done this before. I think no need to go into too many details. But one little detail here for the inductive learning part, we change the update a little bit here because this is what GraphSage does, by the way. It's another method that's updated version from the GCN that works better with inductive learning because we need to be able to predict on new unseen graphs. They talk a little bit about those, but these changes are actually from other papers. I guess we don't need to go into too many details unless we have time. The sampling part they talk about here is to feed Reddit into memory. So they do intelligent sampling proposed in a different paper by Hamilton, who is also an author in this paper. And let's go down.
I have a quick question / comment. So they keep calling this sort of unsupervised learning in the paper, but the way that I think of it is sort of self-supervised learning.
It's
and
similar.
I'm not, because sort of you're creating labels, right? So then
it's a similar
from
idea
the data itself. So
similar idea to doing unsupervised language model pre-training, right?
Okay.
You can see it in a similar way. Yes, there are no labels, but we are making an assumption that sentences make sense. In this case, you're making an assumption that similar nodes, whatever similar means, are near each other. Right? Yes, you make assumption about the data and do it without explicit labels. But yeah, it's like sort of unsupervised.
Because usually, when I've done contrastive learning, usually on image data, we call it sort of self-supervised because you pick one image and then you pick something very different in the data set and you say that's something else. So I was wondering why they didn't use self-supervised. Maybe that term wasn't used back then, or maybe, yeah, I'm not sure.
I think maybe there's no labels in the output. So this is just the features, scanning features rather than labels. So there's no labels involved.
They're not producing labels at all. They're not even learning labels.
Yeah.
That makes sense.
Yeah, but the distinction between self-supervised and unsupervised is hazy sometimes. I think that it's hazy because it's like it seems like there's some amount of effort that has to be done by someone by the designer or the engineer of the network, the researcher for the network, to make it self-supervised that maybe you don't need with unsupervised. I don't know, maybe there has to be an additional design decision, which there is here because the corruption function is a design decision. But anyway, I guess, yeah.
Yeah, okay, so let's look at the last piece. There are a few interesting parts here I wanted to cover, which is, so first, all these models are not deep. They're all 3-layer, 4-layer or so. And they all have skip connections, which is also interesting. They're 3-layer with dense skip connections. I thought that's interesting. And then they call it deep. deep graph Infomax, but they're not really deep, right? And they also have a comment at the end that they found out that for free experimentation, that wider models perform much better than deep ones. But that's not uncommon in graph learning because deep models tend to oversmooth. They average too much of the neighborhood, and then all embeddings become too similar. I thought that's interesting to mention. Another thing to mention is that they also use a fairly simple readout function, which is again average with nonlinearity. But they mentioned that there are other more advanced methods that could be considered for less simple data sets. That too vague. I haven't read this. There's this also diffful, again another way for pooling function. Sometimes it's called pooling, but here they call it a readout. And the discriminator is, well, again, with the nonlinearity is a value, I think. Nonlinearity with a weighted product between the summary and H. The weights are learnable. Okay, a bit of quick results. As we said before, the method doesn't always outperform, but that's not the point. The point is that we can learn meaningful node embeddings that capture global information as well as the local one without oversmoothing and without labels. That's quite useful. If you want to outperform these models, maybe we could do something more advanced than what did they use? Linear regression? No, logistic regression. Sorry, logistic regression. Maybe they could use something more advanced, right? Another experiment I would like to see would be to take, because when you train any of the normal deep GNN models, you also end up with node embeddings. Maybe they could also experiment of taking those node embeddings and putting them through the same logistic regression to compare results, right? Because maybe those GCNs actually learn poor node embeddings or very specialized one for a specific target. So that I think that would be an interesting experiment to judge the quality of node embeddings. But yeah, if the classification accuracy is sometimes better, but not always. Any comments, questions about the performance? No? Oh, cool. Oh, they talk also about this other idea. So randomly initialized graph convolutions. So there has been work showing that randomly initialized graph convolutions are already good, create already good node embeddings, graph embeddings, no, node embeddings, which is interesting because they also argue that perhaps the previous methods using random walks haven't actually been learning much because all you learn is from graph convolutions. So you are with.
Yeah, so one thing I thought that was a really good experiment that they did in the experiment section is where they randomly initialized their method. And then they just, so they created a randomly initialized network and they just used it on their method and it outperformed all of the previous methods. And I was like, man, I wish that other people had thought of doing this when they were developing their methods as well, because it basically means that you have like 6 papers that could have been outperformed by linear regression.
Yep.
Which have very complicated methods. And
so this linear regression, first you need to do the graph convolutions to learn the graph structure. So the node features are not meaningful then, right? But that's what it's saying.
Well, but in this case, they randomly initialized their network, like their encoder, and they didn't train it. There
was no training.
Yeah, they just trained the linear regression, like basically the last layer of the linear mapping, and it outperformed the other methods.
I thought random initialization meant they ignored the node features, the initial input features.
See, it says as such, we also provide as random init the logistic regression performance on embeddings obtained from a randomly initialized encoder.
Randomly initialized encoder. So the encoder has been trained.
It hasn't been trained.
That's weird.
Basically, besides demonstrating that DJI is able to further improve on this strong baseline, it particularly reveals, and that's when they're saying like these other methods probably aren't that good, because
those are the pre-GNN methods, pre-GCN methods, the random walks.
Yeah, so if you look in the transductive and inductive tables, you can see the random init.
Those, right.
It's just randomly initialized it's just a randomly initialized message passing network, neural network, and then they don't even train it, and then they just use those as those things in a linear regression model, which they do train to this classification.
Mm.
And it outperforms all of the other methods, basically.
Does it mean you average the nodes, neighborhoods, random features, which is also existing features with random weights?
So yeah, you take the feature representation as input, you pass it through the graph, you get your H, but your H is calculated using random weights.
Right.
And then
Yeah, I guess that makes sense, because if there is an assumption that those nodes are similar, so their features should be similar in some meaning, in some space, in some ways of some defined way of somehow defined way of similarity. That's cool. Okay, there is also nice TSNE graph here, plot. Basically, the right one is from their method, showing much better separation between classes. So the other two is the randomly initialized DGI and the learned DGI. They both are okay. No, the left one, sorry, is the embeddings from the Cora dataset with raw features without any GNN. The middle one is the randomly initialized DGI, because they look kind of similar quality. The right one is the trained DGI.
So does the left one not use adjacency matrix? Just uses X?
Yes, yes. Just only the raw features, right? So there was training, but no. It says the raw features. Right, this is from the raw features.
Oh, okay. So it does.
I think so. Yeah. Anyway, that really concludes the paper. A lot of interesting experiments, and we are out of time. So I'll stop the recording